Today, I am going to discuss about the Fourier transforms of periodic pulse waveform, rectangular waveform, square, triangular, and sawtooth signals. So, I am going to give some simulations also on these 5 popular signals. So, I am going to show some simulation examples using MATLAB, and I am going to present you the results with numerical illustrations. So first let us consider the theory part of the pulse signal, and here when I call pulse signal, it is like a pulse, narrow pulse, and when I say rectangular, the on period in a cycle is more than the off period. When I say square wave, naturally the on period is same as the off period, and triangular and sawtooth waves are they are not the rectangular waves, they are different waves. Okay, and when I take sawtooth, it is a special case of triangular, and though they are belong to similar class, their Fourier transforms will be totally different. So let us go to the first signal, that is unipolar periodic pulse. Why I am calling this as unipolar is the base level is 0 and let us say it is 1. So let us say it is amplitude 1 volt and 0 volts. So between 0 and 1 the signal is varying. So that is the reason we are calling this as unipolar. If it is bipolar, it has both negative and positive values. Okay, so that is what. Let us consider the first unipolar periodic pulse, and it is a pulse. Why this is called pulse is, here the on period is 2t1. 2t1 is the on period. So this is the on period 2t1. It is less than t by 2. So this is the t by 2, and 2t1 is less than t by 2. That means on period is less than 50%. So that is the duty cycle here. In this case, I am calling as duty cycle means let us say it's a DC here, duty cycle, and this is less than 50%. That means less than, in numbers, in fractions it is less than 0.5. If the full cycle is unity, the duty cycle is less than 0.5, then it is called pulse waveform, and it is a unipolar pulse waveform. So when I say unipolar pulse waveform, if I take a bipolar pulse, you can have equal positive and negative levels probably, and they may cancel each other. But when I say unipolar, so there is no such cancellations. Always there will be some DC, irrespective of the duty cycle. All pulse waveforms have certain DC value. So DC value means, in our case, it is, if I consider this, for example, A0 is the DC value. This is Fourier coefficients basically. So we know that if I multiply these Fourier coefficients by 2 pi, I will get the Fourier transform. Okay. So here whatever I am showing is Fourier series coefficients, and Fourier transform also the values are same, but it is scaled amplitudes you will get. Okay. So A0 is equal to here 2t1 by t. T is the full cycle and 2t1 is the on period. So t on period by total period. This is nothing but our duty cycle here. Okay, duty cycle. So this is naturally, in this case, it is less than 0.5. or 50% I can say. So that is what we have regarding this waveform. And if I take the coefficients, AK coefficients, Fourier series coefficients for k not equal to 0, that means k equal to 1 to 3 etc etc, and k equal to -1, -2, -3 etc etc. So this is basically, we know that it follows a sinc function. In the previous classes we have already discussed this. I am just reviewing here, and I am showing here the sinc function. And when I take individual, so when I take individual impulses here, they correspond to Fourier coefficients. So this is A0, this is A0, and this is A1, this is A2, okay, then A3, this is A4. So A4 equal to 0 here, A4 equal to 0. So fifth coefficient is becoming 0. So here, what is the duty cycle part here? Duty cycle here is dc equal to 2t1. 2t1, that is what you have, correct? 2t1 by t. So in this case, what is 2t1 by t? T equal to 8t1. So 2t1 by t means t by 4. 2t1 equal to t by 4. T by 4 divided by t. So it means I have 25% duty cycle. This is 25% duty cycle case. The pulse is very narrow, and so this is what you have. And the envelope of this one is nothing but sinc function. The envelope of this one is a sinc function with 0 crossings. At multiples of 4. So at multiples of 4. Okay. Now, if I take the second case here, that this is 16t1. 16t1 means, in this case, if you compute as substituted above, I will get t by 8. So that is 1 by 8 is the duty cycle. That means 0.125. 12.5% is the duty cycle in this case. 12.5% means 0.125 in fraction. So it is basically the duty cycle has reduced. The pulse has become half the previous pulse width. Okay, the pulse has a width of half of the previous one. So that is the reason this first null is happening at A8. So this is A8. It is, earlier it was A4, now it is A8. That means the spectrum is stretching more compared to the previous one, because the pulse width has reduced. So once the if the pulse width is reduced, what it means? The spectrum will expand. So naturally the sinc function has expanded now, and here the first null happens at multiples of 8. So let us take this square wave now. In this square wave, we have 2t1. So this is what is 2t1. 2t1 is equal to t by 2, half the cycle. So the duty cycle is 50%. That is 0.5 duty cycle. I mean DC I am using for duty cycle. Then if I take this, because unipolar, what is the average value of this one? This is unity, this is 0. The average value will be somewhere in the middle. That is nothing but 0.5. Average value is, this is nothing but your DC value. So I am representing the DC value by small d, small c. DC value equal to 0.5. So that is what here A0 is nothing but 0.5. But in this case, the duty cycle is 0.5 and DC is also 0.5. Okay. So it is the case of unipolar square wave. Now let us come to other questions. Again here also the envelope. So this is the envelope basically. This is the envelope. This envelope is again followed the sink envelope. The envelope of these coefficients okay. So this is the envelope here, and you are sampling this envelope at k by substituting for k different values. And if you see in this case, the DC value is 0.5 and A2, A4, A2, A4, A6, A8, all even coefficients, even harmonic, the coefficients of even harmonics, they are zeros. If you see here, this is 0, this is A4, this is A6, sorry, so this is not correctly, I think I will write it up. I have to write it this. So this is another 0. Okay. So A2, A4, these are all zeros. All even coefficients are zeros. Then what about odd coefficients? Odd coefficients, first thing is the first value is 1 by pi. 1 by 1 into pi, because this is k pi, because this is nothing but k pi, k equal to 1. Then k equal to 3, you have 1 by 3 pi. So this is k value, 1 by k pi. And they alternate sign. That means A1 and A5 are positive, A3, A7, A11, they are negative, like that, etc. etc. So there are two things here. Within the odd coefficients, they are alternating sign. That means their phase is 180 degrees. The successive, the neighboring coefficients, they change phase by 180 degrees. So that is shown here as a negative values here. This is minus A3 basically. So A3 is minus value. You can see from the list here, this A3 is minus. A5 is positive. A4 is 0. Then A7 is negative, like that. You can see here A7 negative here. A7 is negative. Okay. A3 is negative. Okay. Other things are positives. Now let us move to the same square wave. When I take between 0 and 1, so this is what I have, 0 level here. This is, let us take this as 0 level. This is 1. The average value is 0.5. So in this case, it is unipolar. In bipolar, we have, say, the spread is same. Peak to peak amplitude is same. That is 1. But this side, it is minus 0.5. And this side, it is plus 0.5. So the mean value is 0. So if I integrate this positive area and a negative area, I will get 0 here. Okay. So 0 level is in the middle. So when you see this unipolar waveform, I have a DC value at the center, A0. Okay. Then if I take the bipolar square wave, because DC value is 0, so this is A0 is 0 here, correct? A0 equal to 0. In the middle, A0 is there. All other things, they are intact. They are as it is. All other coefficients are same except for the A0, because A0 corresponds to DC value. This is okay. So here A0 is nothing but DC value, and in the second bipolar waveform there is no DC, hence A0 equal to 0 here. Okay. Now let us move to the square wave with some numerical examples. Same plot I am putting it here, and this is basically by seeing this spectrum. What is this? This one, the spectrum of a bipolar square wave or unipolar square wave. So by seeing this DC value in the middle, you can conclude that it is unipolar square wave. This is unipolar. Okay, by seeing the DC value in the middle, you can conclude that. Now, what is the on period here? On period. First thing, total period equal to, let us say this is a square wave, unipolar, 1, 0. Then what is this total period? Total period is 1 millisecond. 1 millisecond means 0.001 seconds. So this is what is the total period T from here to here, one cycle. Then T1 is T by 4. That means so here in our notation 2T1 equal to T1 equal to T by 4 means what? 2T1 equal to T by 2. So T by 2 is again half of the cycle. So if I take half cycle, what is on period now? On period is T by 2. That is nothing but 0.5 milliseconds. 0.0005. Zero point zero zero five milliseconds. Sorry, directly these are seconds only. So these are seconds only. Now, if you see here, this spacing, for example, this spacing between successive harmonics is nothing but, let us say, F0. What is fundamental frequency of this here? F0 equal to 1 by T, that is nothing but 1 by 1 millisecond, that is nothing but 1 kilohertz. So this is F0 equal to 1 kilohertz in terms of linear frequency values. So let us say this is F0, linear frequencies, and this is nothing but how you get this F0? Omega naught is nothing but 2 pi F0. Okay, then omega naught by 2 pi. So this is nothing but omega naught by 2 pi. If I put, I will get the F0. So this is the unit for F0 is H, whereas for omega knot, that is angular frequency is radians per second. Here it is cycles per second. Now between this is the fundamental frequency, right? So what is the separation between this? This is f naught. So this axis is linear frequency axis. Okay, and this is what f naught, how you compute here. This is nothing but 1 kilohertz for us in this case. This is nothing but 1 kilohertz for us. So k equal to 0 means 0 hertz. K equal to 1 means 1 kilohertz. K equal to 2 means 2 kilohertz. This corresponds to 3 kilohertz. So like that. Okay. Now 3 kilohertz. This is 4 kilohertz. This is 5 kilohertz. Fifth coefficient means A5 means 5 kilohertz. So like that you have in terms of linear frequency. Now same thing I am taking and I am making the time period half. So this is what is previous cycle for us. And now what I am doing? I am taking the waveform like this. So what is done here? It is the period is half. The period is half and it is a square wave. So what it means is the period itself is 0.5 milliseconds. This is the period, and on period is 0.25 milliseconds. Okay, period is 0.5 and on period is 0.25. So what is the frequency here? Fundamental frequency 1 by 0.5. 1 by 0.5 milliseconds. Okay, this is milliseconds. So 1000 divided by 0.5, I will get 2 kilohertz. This is 2 kilohertz. The fundamental frequency is 2 kilohertz in this case. So each harmonic is separated by 3 kilohertz. This is 0 hertz. This is 2 kilohertz. 2k, I am writing 2k or 2 kilohertz. Then this is 4 kilohertz and this is 6 kilohertz, like that. Okay, so here you can see that this is the DC value. Let me change the color here for better visualization. This DC is here and this first frequency has shifted towards right. The space has widened. Earlier it was 1 kilohertz, now it is 2 kilohertz. Okay, and similarly the odd coefficient A30, it has moved to this place, I mean to this location. So basically what happened here is you have reduced the time period and it is a square wave. So half of that is a on pulse. So naturally, because the total waveform has compressed, I mean if you take one cycle, it has compressed, automatically the Fourier spectrum has expanded here. Okay, these are Fourier coefficients I am seeing. When you say Fourier transform, you have to talk about the envelope of this one. Okay, envelope, but envelope exists only at these locations. And when I say envelope, when I say envelope, it won't mean that. So this is the envelope. I mean, Fourier transform is like this. But when I say envelope, it is not that. So these frequencies are not there. Okay. So only this frequency is available. This frequency is available. So in between there are no frequencies. So basically, in fact, to be frank, to correctly write, I should draw like this. I should draw like this. These are all. It is a continuous curve. Fourier transform is a continuous curve. It goes up, comes down, and again it goes down, again it comes up. Okay, like that. So in fact, there is no between the harmonics. There are no frequency components available. Okay, but the curve is continuous. So now I'm going to describe you some simulations. Fourier transform of a periodic pulse, if I take. This is what you know. This is a pulsed waveform. I am showing here only the amplitudes, modulus of this one. So the all sign information or phase information is not lost in this. I am showing the magnitude waveform. And here, what is here? Pulse width is, I am calling this as pulse width. Let us call this, earlier it was 2T1. Okay, 2T1, I will give a name as tau. I call it as a tau. So this is equal to 0.01. 0.0, sorry, 0.001. Okay, let me erase this. So this is 0.001 seconds. Now what is fundamental frequency here? Fundamental frequency equal to, what is fundamental cycle period is 0.005. So that is small tau is the on period, capital T is the cycle period, that is 0.005. Okay, 005. So what is the duty cycle here? Duty cycle is, how much this is? Duty cycle is tau by T, that is equal to 0.001 divided by 0.005. So it means 1 by 5, that is nothing but 20% duty cycle. In terms of percentage, I should write 20% duty cycle. Okay. And what about the frequency? Frequency is 1 by T, fundamental frequency. And I should say fundamental frequency. I should not say the frequency of pulse wave. Okay, pulse wave, rectangular wave, I cannot say frequency because it is a combination of so many frequencies. See, this is the DC value, first frequency, second frequency, third frequency, fourth, fifth, sixth, seventh, like that. There are infinite number of harmonics are there. So when I say frequency, that is applicable only for the sinusoidal waveform. Okay, so it comprises so many infinite number of sinusoids in theory. Okay, but practically, if you take some finite, the 10 odd harmonics, that must be sufficient for a square wave. And if it is a maybe 10 cycles, 10 nulls, if I take, that must be okay for the pulse waveform. So what is F0 here? 1 by T, that is nothing but 1 by 0.005, that is nothing but 200 Hz. 1000 divided by 5, that is nothing but 200 Hz. Okay, so 200 Hz. If you see here, this is the spacing. So this is 200 Hz, scale is H, this is 300 Hz, this is 200, sorry, this is the second harmonic is it is 400. Okay, this is 400, then this is 600, this is 800. So first null is at 1000. This is 1000. First null. So 1000. This is 1000. So what it means is the spacing between the successive harmonics is 200 Hz. What is this 1000 Hz? 1000 Hz, how you got? So this is I can say that bandwidth. I am calling this as a bandwidth between first null, BWFN, bandwidth between first null. So this is equal to 1 by tau. 1 by tau. What is tau here in our case? Tau is nothing but 0.0001 seconds. So this is nothing but 1000. That means 1 kilohertz. So 1 kilohertz, because so spacing between successive harmonics depends on the period of the waveform, and the first null is related to the on period, that is tau. 1 by tau is nothing but your first null. This is nothing but 1 by tau. Okay, this is one-sided spectrum I am showing. If I show other side, I have negative spectrum. This side will go like that. Okay. So let us move to the next one. In this case, I have described you how to understand this spectrum. Now in this case, pulse width is reduced. It is half. Earlier it was 0.001. Now it is half of that one. So when it is half of that one, that is the reason 1 by tau is double the previous one. So this is nothing but 1 by tau. In this case, 1 by tau is 2000 H. So see, compared here, this is, compare this with this null. This was the previous one. For comparison, if I take tau equal to 0.001, now it is 0.0005, half of that one. So in this case, this is the first null. In this case, this is the first null. So naturally, you can, as the pulse width reduces, the bandwidth will increase. Bandwidth means bandwidth between the first null. But in fact, if you want to take 3 dB bandwidth, this is log 1. This is called 0 dB and 0.7 times. So let us say somewhere here, 0.7. Let us say somewhere here. I mean, from this plot. So this could be the 3 dB point. Okay, 3 dB point. Actually, this is minus 3 dB. I should say that this is the 3 dB bandwidth. So 3 dB bandwidth of the signal is 1000 approximately, because this is simulations, you have to really calculate that one. So as per the graphical information, whatever we have, this is the 3 dB bandwidth. And what about this one? This is nothing but bandwidth between first null. There are two bandwidths we are defining. Bandwidth between first nulls. Okay. I mean, between first null means I am taking one sided 0 to 2000 here. Okay. So this is what you have. And let us understand the other waveforms also in the same way. I am taking again rectangular. This I am calling it rectangular because this is 0.004. So this is whatever I have drawn here. First cycle. This is the on period. This is the middle basically. When you expand this, so how this waveform is looking is something like this. Something like this. And this is duty cycle is 80% duty cycle basically. 80% duty cycle means 80% of the time it is on, pulse is on, and the remaining 20% of the time it is off. This is the duty cycle here in this case. Okay, so here the pulse in terms of pulse widths it is 0.004 and cycle period is 0.005. So when I say cycle period 0.005, what is F naught? F naught equal to 1 by 0.005. So this is nothing but 200 Hz. 200 Hz is the fundamental frequency. And what about frequency at first null? I call this as a frequency at first null. Okay, if I take between 0 and first null, it is called bandwidth. If I take single value at first null, I am calling that as frequency at first null. So there is nothing but divided by 1.00 because 1 by tau 1.004. So what is this? This one? This is 1000 divided by 4. That is nothing but 250. In this case, it is nothing but 250. That means very close. The first null and the first harmonics both are very close. So that is what you see here. See here. This one is, sorry, not that one. So this one is 200 and this is first null. First null is this. This is 250 because we have increased the pulse width on period. We have increased naturally. When the time waveform expands, the frequency should compress. So that is the reason the first null is only at 250 Hz. Now take this. It is a square wave again. Pulse width is 0.001. When I say pulse width, immediately I can compute frequency at first null. Frequency at first null equal to 1 by 0.001. That is nothing but 1 kilohertz. Correct? That is nothing but 1 kilohertz. 1 kilohertz. Now this is 1 kilohertz. 2 kilohertz is 1000. That is second harmonic not present. Fourth harmonic not present. Sixth harmonic not present. But you have the third harmonic present and fifth harmonic. All odd harmonics are present here. All even harmonics are zeros, nulls. Okay, so that is how. Then what about the period? Period is 0.002. So it is equal to F naught. Equivalent F naught equal to 1 by T. 1 by T is 1 by 0.002. So there is nothing but 500 Hz. 500 Hz here. So when you see this 500 Hz, this is 500 Hz. Correct? First harmonic is 500 Hz. So each spacing between successive harmonics is nothing but 500 Hz. Okay. And this is a unipolar periodic waveform because this is 1 volt and 0 volts, 0 and 1. Now let us move to the next one. Here what I have done is same thing, same waveform, whatever I have shown here this previous spectrum. Here there is a DC value, and what I have done here is I have normalized, I have normalized the spectrum so that the highest is 1. That is what I did so far. So that's why in the middle always it is higher. That's why it was showing 1 always in the simulations. Now when I take the bipolar waveform. This is nothing but bipolar waveform. Why it is bipolar waveform? Because it has both polarities. That is minus 0.5 plus 0.5. Mean value is 0 volts. Okay. So if there is no mean value here, A naught equal to 0. So this is not appearing at all. Here there is no A naught, it is 0. A naught is 0. So but here A naught is greater than 0. That means something is there here. So when I remove the DC, instead of 0, 1, when I used minus 0.5 to plus 0.5, what happened is, now this is the A1 and this is the highest value, highest magnitude. Then when I divide the total spectrum by the highest amplitude, I got unity there. Okay, because I have removed the highest one DC value here. So I got A naught equal to 0. So A1 is the highest one. So I am normalized this value so that the highest value is always 1. That is what I did purposefully. I will explain to you why I did it. This is 1. This is third harmonic. What is the height of this one? See here. If I see this is 1 by 3. Then this is 1 by 5 because this is the fifth harmonic. 1 by n is the amplitude of this harmonic. So far we talked about only the frequency spacings of this, but now I am discussing about this amplitudes of this harmonic. This is seventh harmonic, 1 by 7. Okay, 7 into 500 basically. 7 into 500 is 3500. So this is nothing but 3500. All odd harmonics are present here. Then 8th harmonic not present. Okay, 10th harmonic not present, and this is 1 by 9. If you see the values, so this, if you see the values exactly, they are matching. See here, A naught equal to 1 by pi. Remove this 1 by pi, call this, divided all these values by 1 by pi. Then what I will get? This 1 by pi will go, this pi will go, this pi will go. So I am left over with only 1 by 1, 1 by 3, 1 by 3, 1 by 5, 1 by 7. So normalized coefficients these are. And the amplitude of the harmonic is inversely proportional to the, because if I take 1 by pi as a constant, what I can write here? AK amplitude I am taking because minus and plus it is collapsing in the magnitude spectrum. It is proportional to 1 by k. That means inversely proportional to the harmonic. That means as the harmonic number increases, its contribution to the waveform, it is coming down basically. Okay, so this is 1 by 11, this is 1 by 13, 13th harmonic, this is 1 by 15th harmonic. Sorry, 15th harmonic means 1 by 15, and this is 8000. Why this 8000 here? This is nothing but because in my simulations, though the curves appear because of graphics, the curve is appearing smooth, but these are all discrete things. In fact, this square wave is a discrete square wave, and I have generated the square wave values at discrete samples of time. So discrete time signal basically, because it is not possible to simulate continuous time signals on digital computer. So whatever we have are all digital computers. So whatever I have done so far, they are all discrete time signals. So I mean, many people, they confuse with this, because just because the plot is continuous, you should not think that because digital computer is generating only the discrete values, you are adding the tips of these discrete values so that you get a continuous curve. It is the magic of the graphics package, not actually the values are continuous.
Like, share and subscribe. Hit the bell icon for more updates.